Okay, cool. So, the idea for today is to extend what we did last week to, I think, extend this project to support two new features. The first one being to draw our first 3D shape. So, I will show how to draw a cube, and differently than what Professor James did. I'm gonna draw or make this cube out of kind of a raw list of vertices. I think in his approach, if I'm not wrong, he proposed to draw cubes out of triangles that we already had in a previous class, and then um, and then that might cause some performance issues because essentially for every triangle you have a draw call. But what you could do is kind of decrease that amount of draw calls by having all the vertices of the cube in one single attribute buffer and then calling one draw for that whole list of vertices as opposed to going for each triangle. That should speed up your code of, by a good amount. And this, I mean, for every cube, you're probably going to decrease or speed up every cube by a factor of how much. So every face has two triangles who have six faces. So it's like 12. You can might speed up like 12 times the amount of time you normally use for rendering one cube by simply doing this approach we're going to see today. And this is an option. I know it's not that this is mandatory, but if you face performance issues on your side, it's a good way to start improving the performance of your code. And after that, what I want to show is kind of introduce a topic that we're going to use a lot or a lot in the next assignment, but which is the idea of having like more data per vertex. And what do I mean by data? I mean by, for example, we right now we pass an x, y, and z position for each vertex, but we could, for example, pass a different color at each vertex and then assign a different color per vertex. And we will see that as a general way of sending multiple data elements per vertex. Um, so I'm gonna explore these two ideas today, and they're gonna be used like a lot from now on. So hopefully that helps. I hope this is gonna take less than 2 hours. So if we finish earlier, we can discuss personal questions if you guys have. Okay, so let me get started. Uh, have you guys seen my project? So were you here before in the last labs, or have you seen the recordings of the lab sessions? Yes or no? Okay, Eric, were you here, or did you see the last lab section on YouTube? Okay, I asked because um, I'm gonna work or I'm gonna build this code on top of what we built so far. So if you get lost or if you don't understand something, uh, feel free to stop and ask a question. Okay, but essentially what we have is what we see here in the screen. I'm going to refresh my browser, and we have two triangles. One is actually moving to the right, and one is just rotating around. Uh, and we did this in a very nice uh, general solution where we have a triangle class here, and this class defines the vertices of the triangle, and then also adds a model matrix, a translation matrix, a rotation matrix, and a scale matrix for that triangle. And then we have these functions here, translate, rotate x, rotate y, rotate z, and scale, that operate on these matrices. So our triangle now has this flexible way of being translated, rotated, and so on. And in our assignment 2.js, which is like we have our main function here, and we can easily create triangles like this, right? And we can easily draw triangles by just calling draw and then passing the triangle as the argument. And this draw function is very generic, so it supports any object. We're going to extend. We're going to see that um, in this lab that we're going to be able to reuse this whole structure for drawing other shapes and including 3D shapes. Okay. Any questions before I get started with the new code? Yes or no? Okay. Okay, if you don't say anything, I'm going to assume you guys are good. So I'm going to keep going. Um, okay, the first thing I want to do is I actually want to create a generic class for geometry. And so I'm going to make a new file here and call this file geometry.js. And oh, and this is going to be a class uh, geometry. Uh, and what I'm going to do here, I'm going to copy the whole code from the triangle. Actually, let me just copy this whole thing. I'm going to change the name here to geometry. But I'm going to remove these vertices. I'm going to keep the definition of the vertices property, but empty. Okay, so this means that the geometry has a list of vertices, but I'm not specifying anything. It can be any set of any list of vertices. But also every geometry has these transformation matrices that I'm going to use to transform the geometry. So this is just a generic definition of geometry. And essentially what I'm going to do is I'm going to say that a triangle extends geometry. By doing this, oh, every time, geometry. But by doing this, I now inherit all the properties and functions from geometry. So I can erase this whole thing here because I actually getting this now from geometry. But I'm keeping the vertices because this is the specifics of triangle, right? The only thing that changes is that a triangle is a geometry with this list of vertices, okay? And here I have to call super, which is only when I call this super function, essentially I'm calling this constructor here. So we have to put it there. So just because we have to manually call this constructor, okay? So by doing this, now we have a specific geometry called triangle. Okay, so let me fix my HTML to load the geometry class, okay? Because we're gonna need this. So by doing this, I haven't changed anything, honestly. I don't think I have to change anything. Uh, I don't think I'll have to change anything in my main function because yeah, I can still call this, but it turns out now that this is actually extending geometry. It's just a different kind of class hierarchy. Let's reload the page. Okay, there's a problem. Geometry 38. An expected end of input. Okay, I forgot to close this curly brackets here, and that's it. So that was the only problem. Well, so now we just added this extra superclass here because I want to start extending this and having other shapes. Um, so let me check. So someone is asking here. So Eric is asking here in the chat. So this would be the same for circle and points, correct? Or points is a geometry class itself. Uh, points are different because they are drawn as points and not as triangles. I think this geometry is going to be used for every single shape that can be drawn using triangles. Unfortunately, so points, it's a more, I think it's a specific case um, because a point, we don't draw a point as triangle, we draw a point as a point. So I would probably keep another class here for points. But what you can have is something like this. For example, we can definitely now have a square. We can have a square function, a square class, sorry, that extends geometry, right? And then our job, the only thing we have to do is, again, call super here, but you have to define the vertices list to be a square. And this is going to be a new float 32 array. And here we're going to have to pass the vertices to make a square. Okay? And we can make this one. It's going to be, so remember that we have to define this geometry, or every geometry, in terms of triangles, right? And why? Why is that? Because here in our draw call, where is it? Because here we are calling draw arrays triangles. This means that the graphics card is going to try to interpret this list as triangles. Okay, so that's why for triangle is very intuitive, right? Because we are drawing one triangle, but for a square, we have to break down a square into a set of triangles. And well, it turns out that we can draw a square using two triangles, right? Imagine one triangle here going from this corner all the way down here, making this bottom triangle, and another triangle going from this top corner here and closing here. So we only have, if you can specify a square out of two triangles. And that's what I'm going to do now. I'm going to start with this top left corner here. And this top left corner is equals to, that's -1 in the x. So center is 0, 0 is here. So this is -1, right? And 1 on y. And then z 0, because it's, so I just specified this is the top left corner. Oh wait, I think yeah, so minus, and this is -1, -1 now. So this is -1, -1, 0. And this is the bottom left corner. Okay. Now I'm going to get this guy. Okay, so I'm making this triangle here. This is 1 on x. -1 on y and 0. Okay. So now this is our first triangle. right? Now we need to specify the second triangle. However, we can't reuse. We're gonna have to reuse these points. We're gonna have to, or these vertices we already created, we're gonna have to start again. Because again, this is one triangle. Now I need a second triangle, which is gonna have this vertex again. So see, unfortunately, I can't kind of reuse this. I have to kind of copy it to make the second triangle. So this is gonna be this guy, the the top, so the top left corner, the top right corner, which is 1, 1, 0, and the bottom right corner, which is 1, minus 1, 0. Let me align these numbers. So let me write this. So this is the bottom right corner. And again, then I have again the top left. And this is the top right. And this is the bottom right. Okay? Does this make sense? Yes or no? Okay. So now we specified two triangles, right? We can even say that triangle 1, and this is our triangle 2. So now, by simply doing this, we have a square that we can create here in our assignment 2. We can now come here and say square 1 equals new square. Well, let me make sure I'm loading this in my HTML. No, I'm not. So let me load this square file. And so now I can definitely call a new square here. And I'm gonna now, and here I can easily now call draw square. I'm gonna comment these guys out just to make it clearer. Oh, geometry is not, again, a typo. This looks like a typo here. Yeah, all the time. Geometry. Okay. There you go. So we see this kind of the whole screen blue because the square is taking the whole screen, right? So if I want to scale my square, remember that square is a geometry and geometry has a scale function. So I can just come here and say square 1 dot scale, and I'm going to scale it by 0.5. So we're going to just reduce the size by half. Now, if I refresh the page, I get a nice square on the screen. Okay, and we can use the same transformations. If I want to rotate the square again, I can rotate the square by reusing this code here. For example, square 1 rotate, and let me comment this out. If we just do this square 1 dot rotate z, and we have this variable rotation z here, that's equals to 0 in the beginning, and then every frame we increment this variable by 1. So we're going to see this square rotating by 1 every frame. Okay, there you go. And again, we can use also the translation on the square if you want, and it's going to work just fine, right? We can do translation x here and have this translation x variable. Here we're going to increment the position of the square by 0.01 units to the right. So this square should move to the right and also rotate, because I'm also doing rotation here. Let me remove this. So I'm rotating now and also translating to the right. See? So we just got, we borrowed all the properties from our geometry by extending it to be a square. Okay, so I think this is a very nice and elegant solution to this problem of having geometries, because now we can create any new geometry by just extending geometry and define a list of vertices in terms of triangles. And this is true for circles. If you want to do a pyramid, if you want to do any geometry, a cylinder, anything that can be drawn as a set of triangles, you can specify here. Of course, and you'll see that for 3D shapes, it gets kind of painful to define by hand all the vertices. For example, a cube, it's going to has 6 faces, so it has 6 times these many vertices, and we're going to have to specify this by hand. But it's just once. You just have to do it at once, right? Because you can always scale and translate and do all the transformations using these nice functions here. So okay, so I'm gonna move forward by drawing a cube now. So this is gonna be our first 3D shape. Okay. First, I just want to organize this project a little bit. So I'm gonna make a folder, call it geometries. And I'm gonna move these guys because we're gonna start having a lot of geometries, and I want to have everything inside geometries. I'm gonna make sure just close these things. Here now I have to add the path geometry, geometry. I don't know why I have a problem with this word, geometries. Okay, geometries like this. And yeah, so that's it. Let me make sure. Okay, it still works. Okay, I want to now create a cube class. Class cube extends geometry. Okay, so now we have to do these as vertices. Those vertices, new, float 32 array, and then have here. Now we have to define, now I think I'm gonna copy this comment here and say, so make it clear, we can draw a cube using 2 triangles per face, right? Because every face is a square. So this means that we're gonna have 6 times, so you have 6 times 2 triangles, right? So you're gonna have 6 times 2 triangles, and this means 6 times 2 times 3 vertices, because every triangle has 3 vertices. Okay, so this is 36 vertices. You're gonna have 36 vertices here, which means this is gonna have, we're gonna have 36 lines. Every line here is one vertex, right? So we're gonna have to define a triangle 3 here, right? and then have, and this is gonna, so this is part of our, this is our front face. We can think of this as our front face. And then we're gonna have to make maybe the right face. And then at the right face, we're gonna have a triangle 1 and 2 as well. Right? And then we're gonna have to do maybe the left face, and then the bottom face, all the faces of the cube. And this is gonna be very painful, but I've done this myself. So I'm gonna copy. I have this like list here already saved because I don't want to spend that much time um, doing this whole thing. So I'm gonna copy this thing here. Just a second. Let me see if I can copy this right. Let me make sure. Okay, let's see. So I hope, because the way I copied this, I'm gonna have to erase the comments. Just a second. Oh yeah. Okay. Hopefully that makes sense. So this is my right face. This is my left face. Vertices, 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 vertices. Oh yeah, actually the columns are not here. Or semicolon, sorry. Here, oh here as well. 1, 2, 3, 4, 5, 6. Okay, so yeah, unfortunately, gonna have to make this whole list here, which is a little bit painful, but it's very efficient to do this way because it's to hard code all the vertices of a cube, and keep in mind that this cube is centered at the origin of the world, and it has size 2 because every face goes from -1 to 1, which is 2. So -1 to 1, we have a size of 2. Um, does this make sense? This whole list here? Yes? Okay. All right. So this is a little bit different from what James did. I think James used the triangles to draw these cubes here, and now we have this whole list. So you have this whole list of points. So this is we have to visualize this. It's hard a little bit, can be a little bit hard to visualize, but this is the right face of the cube. So this is where is the front. Front face is here. So front face is the one we did here in the square. It might be in a different order, but this is the front face, and this is going to show here. So I wanted to, if you didn't understand these numbers, I wanted to visualize this in 3D space. What are these? Where are each of these vertices? And remember, every line is a vertex. Okay. Okay. So now that's it. Again, it extends geometry. Now you have a cube for free. So if we go, we have a cube in the same way as we have a square. We had a square. I'm gonna come. We can make a cube one like this, and if I draw this cube now, again, what I expect here, because it is a cube and it has size 2, I'm gonna see the front face covering this whole the whole canvas here, because that's how you define the cube, right? We defined it to start from here. So this face, the front face, is exactly the square, right? It's going to be the same effect of the square. We're gonna see the whole screen blue here, but it's a cube now. Cube is not defined, yes, because we haven't loaded the script. This is cube. So if we load it now, there you go, right? I see the front face of the cube here on my canvas. And of course, it's not different from a square now because we can't see in 3D. We are just seeing the front face. But let's try to visualize this. So what I'm gonna do is first of all, I'm gonna also scale this cube, scale by half. Same result again because we are seeing only the front face of the cube, but now we have the other faces. And let's rotate this cube to see what we get. I'm gonna use the same idea. Actually, the same function here, rotate, but for cube 1. And I'm gonna comment the translation. I'm gonna keep just for reference, I'm gonna keep the square here as well. So if you want to play with this later, you can just uncomment this line. But now we're gonna see the cube rotating. Okay, so this is rotating on Z, right? Z is this axis going inside the canvas. So Y is this axis, X is this axis, and the Z axis is going in the canvas. So we are rotating around the Z here, right? And this is exactly what I'm saying. I'm saying rotate Z. But what I can do is now is because it's a cube, I can also rotate this around Y. And Y is this axis here. No, so now I'm actually rotating the cube around the y-axis, which is this y-axis here. And what we see is, it's kind of interesting, right? We see kind of a rectangle shrinking up and down, right? It goes a little bit up and then it shrinks down and then it shrinks up. But what's happening is like we are not seeing the edge of the faces because they're all the same color. But picture an edge right here. So we are not seeing the edges of the faces. So we see this kind of rectangle, or sorry, this rectangle shrinking up and down. So to visualize this as a cube, we're going to need to give different colors to each individual face. Okay, so then we can actually visualize every face instead of just seeing this whole blue object. Okay, and that's what I want to do now. This is the second topic that I wanted to talk about, which was like how to give different colors for different faces. Before I do that, do you guys have any questions? Yes? No? So the question is there a way to actually see the edges? Yes, there is a way to draw the wireframes of this cube, which is possible, but that's not what I want to talk about today. But there is a mode of drawing where you can see the kind of the edges of your geometry. Yeah, there is a way. So so what I want to do is paint every face with a different color. And here's the problem. So far, we have seen, or we have used this uniform here to give the color to the object. So for example, and this uniform U color is mapped to this array here, right? So if I change the color here to be red, all the vertices get the color red. So then I see again the same problem. It changed it to red, but all the vertices have the same color. What I want is I want I want that given a face, let's say the front face, I want the front face to have one color and the back face to have another color, and so on and so forth. And we can't we can't do this with uniforms because uniforms again they work for every vertex, right? So it's one global value for every vertex, and now you're going to need a different value per vertex. And we know we can use attributes for that, right? Attributes are variables that are specified per vertex. So what I want is something like this. I want to create an attribute. Let me write this down from scratch. I want an attribute, a vector 3, called a color. What? Okay, a color. I want to somehow create another attribute that, and remember that attributes can only be created here in the vertex shader. But somehow I want to create an attribute here and give it as color down here. I want something like this, right? I want to give one color per vertex. Same way I have one position per vertex. I want one color per vertex, and I want to give this color here. Okay, does it make sense? I'm going to go very slowly here because this is a key concept that a lot of people get confused. So make sure you understand this. The problem is, again, I can't define this attribute here. It's not allowed. You're going to get a runtime and maybe even a compiler, like a compiler error, a compilation error, sorry. So yeah, so someone asked in the chat, Eric, do we use varying? Perfect. That's why we use varying. That's why varyings exist. You're gonna use a varying variable to pass this data from the vertex shader to the fragment shader. I'm gonna call this v color, just to v for varying, okay? And in my main here, inside the vertex shader, what I do is essentially I copy v color to be equal to a color, okay? And now remember that so variants can coexist in both, or actually they always coexist in both shaders. So I can create here this variant, same name, exactly same definition, v color. Okay. And just because I did this here, inside my main function, I already got the a color set to v color. So at this point here, v color is already equals to a color. I don't have to do it again here. So it's already equals to a color, so I can just do this. So now that's it. So now in terms of the shader code, that's the only thing we need to do. Is it clear? Cool. And note that again, vcolor is a three-dimensional vector because you're gonna pass RGB here, and we are just casting. In our previous uniform was also a vector 3, so but you're not using it anymore. We can delete this later. Let's keep it just for because we have it. Then we can maybe delete this later. But we are casting this to with passing alpha or transparency to be 1, but we're gonna specify only RGB here. Okay, that's it for the shader. Now we have to pass or specify a color per vertex. And this is also like a very common point of confusion for students. Let's try to go very slow here. How does it work, right? Remember that for position, well, where do I define the position? If I go to my cube, here's my position, right? This is one vertex. So this means that at some point, my GPU is going to assign this vertex to this variable, a position. But now what if I want a color to be sent with this vertex? Well, what I can do is I can pass a color here. For example, red. I'm going to comment this here with color, with red color. See, if I give this red color to everyone, let's make this blue. Let's make this guy the next face. So this is one face. Okay, this is one face. This face, in this face, all the vertices have the color red. For the left face, I want all the vertices to have a color blue. Or green, sorry, with green color. Because 0, 1, 0, red, green, and blue. Okay, so this is only green. And I'm gonna make this now the back face with blue color. So same idea, 0, 0, 1. And I copy this whole thing. Now let's make the front face, I don't know, white. Which is 1, 1, 1. Okay. So I'm literally passing one color per vertex. Okay. And from the top face, we can give maybe a combination. I don't know if this is, I never know. It's magenta or something. Yeah, but we're gonna give this combination of red and blue. And the next one, we're gonna, or for the bottom face, we're gonna give a different combination. Maybe with all ones here and zeros on the blue channel. Now we have every single face with a different color. I know this is kind of crazy, right? I mean, it's a lot of numbers in here, and we are hard coding the colors. But this is just an example, just to show how this looks like when you're defining the data, or defining the geometry, sorry. Now see that every vertex has a color associated to it. We can even maybe split this with commenting, oh, I won't be able to do this. We first three vertex position, XYZ, and second three color RGB. Okay, and this is for first three elements. Second three element, or Yeah, second tree is kind of weird, but it makes sense, right? Does it make sense how this works? Okay, so now we have one color per vertex, and you see that we kind of carefully picked these colors to be the same in each face, right? We could have messed with these numbers in a different way, but we picked it in an arbitrary way that every face is going to have the same color. Okay, so there is one last thing to do, which is, so this is our third and final step, which is here we have to set up a new vertex, a new, not a new vertex, but sorry, we have to set up our buffer, yeah, to get, not to get the varying location, but you're gonna have to assign those, we're gonna have to assign these three numbers here to the variable a color, which then inside the shader is gonna be passed to the varying and then passed here. So we're gonna have to assign a color to read the three last elements of every line here. Okay, and how do we do that? Again, now you're gonna, here is how, remember when we set up our vertex buffer using these lines here. So remember, I create a vertex buffer, I bind the buffer to be an array buffer, and then I get the position for that, get the variable a position, and then here exactly in these two lines, I tell the GPU how to read the position. So in these two lines, I was telling the GPU to read starting from 0 and reading 3 elements. So now you're gonna have to create, we have to set up the a color variable. I'm gonna get this variable gl.get attribute location, gl.program the variable a color. Okay, and now we're gonna do something similar to this. Okay, gl.vertex vertex attribute pointer. Okay, so this is the function that tells the GPU how to read, how to interpret every line here. First of all, what is the size of the line and how to read the variables in this line. So in this, so index here is always the location of the variable. So it's a color, right? Look at, it's similar to here, a position. Size is the dimension of the vector representing this color. We know it's 3 because again, a color has 3 dimensions here. So this is 3. Okay. The type of each element is also GL float. Okay. Because these guys are also floats. I don't want to normalize this, so I'm going to pass false here. So now it's another also very common point of confusion for students. So for the first time, you're going to actually use these numbers here, stride and pointer. So before we had only 0, 0 here, and this works when you only have one attribute, which is the position. It was the position before, but now you have 2 attributes in the same vertex. So we're gonna have to tell the GPU that the size of the line is now 6 and not 3. So the size of, what do we mean by line here? The size of a vertex is 6 and not 3 anymore, right? So to be very consistent, here we should have written 3. It's redundant when you only have one attribute, but we should have written 3 here because before we only had 3 numbers. Or let's look at our square here. Right here, this is how it is. How it currently is. We are changing this right now, but before we had 3 numbers per vertex, so we should have written 3 here. But now we have to write 6, both here and here. And why 6? 6 because this is the amount of, we can think of this as the length of this line or the amount of numbers in a vertex, right? Or the size of the vertex. You can think of this in these different ways. Um, so this is 6 here. And this is still 0 because the second number pointer tells the GPU where to start reading in that line or in that row, sorry. So for example, the size is 6 and the A position, I want to read starting from the 0 index. So starting from here, read 3 numbers, right? So look at see here, starting from 0, read 3 numbers. So this is for the A position. And because of this line is now like this, sees 6 and 0, the GPU knows that it's going to read these 3 numbers, and the vertex is this size. So I'm going to read again. So imagine like this. I read starting from 0, 0, 1, 2. So these are 3 numbers. Then I go to the next row and I read 0, 1, 2. Next, this is another position. And then this is another position. This is another position. This is another position. So because we did this now, because we put 6 here, the GPU knows where the position starts. Starts at 0, jumping from 6 to 6, always read 3 by 3. And for the color, the pointer is 3 because, again, the vertex has 6 elements. 0, 1, 2. I start at 3 and I read 3 elements, and this is going to be my color. See? Let me close this square for now. Again, line has 6 numbers. I'm going to start at the 3rd element and read a block of 3. So first line, 6. Start at the 3rd element, 0, 1, 2, 3, and read a block of 3. Second line, 6, size 6. Start at the 3rd element, 0, 1, 2, 3. Starts here. Read the color and keep going. Jump 6 elements. Start reading the color here. So this is it. So now we just create a second attribute using the same buffer. So it's the same vertex buffer. We just made a second attribute. That's how you do it. There's one last detail that I'm gonna do before we ask any questions, which is it's just a little technical detail. Is that you have to multiply here these numbers by a float size. And this is because the CPU and the GPU, they're 2 different processing units. So and these numbers are specified in bytes and not, so actually in bits. Yeah, I think this is, no, in bytes. So this number is specified in bytes and not in kind of um, index locations or size. So the size has to be specified in bytes. So we need to get the size of the float in bytes and multiply by the size we need. So we essentially we have to, and the way we read the float size in JavaScript, one way is by typing this float 32 array dot bytes per element. So this turns out to be 4, I think, for float. So I think float 32 is represented with 4 bytes. So here we're going to multiply all these numbers by float size. That's the only detail. We need to do this, otherwise, because this number is interpreted, this number here, this argument is interpreted as a number of bytes. Okay, again, this is a little bit complicated, but did it make sense? Okay, good. Okay, great. Yeah, so practice this. We're gonna, in this course, or in this class, we're gonna have to create other attributes in the future. For example, if you want to map a texture to the object, you're gonna have to pass a second attribute or another attribute for texture. So for texture mapping, so we're gonna have to exercise this later. Yeah, so I got a question here. So float size wasn't necessary before because it was only one attribute. Yes, so there was this special case before we only had one attribute, so there was no big deal. We didn't have to worry about that, but now we have to worry. Honestly, before, to be consistent, we should have actually this. If we had this before, it would work the same way. It would work the same way. And we can show, maybe we can even show that with, not with the cube, because the cube now has all these numbers in it, but the square and the triangle, maybe I can still draw a triangle with this code, with this thing commented out. Let's see, I might get errors. Let me just try. I try to draw a triangle. Oh yeah, wait. If I change this, if I change here to be the uniform color, yeah, there you go. So see, we should have exactly this before. We should have, instead of 0, we should have this. Because before we had 3 elements, the triangle still has it, right? The triangle only has 3 elements per vertex. So but it turns out for one attribute that's not necessary. But that's, to be consistent, we should have written this 3 and then start reading from 0. But let's go back to having colors now. 6, 6. See that if you try to draw as it is with the number 6 here, if I try to draw my triangle, I'm going to get a problem because I haven't specified the colors here and the attribute is expecting it. So I'm going to get an error. If I try to draw the triangle with the 6 here. Here as well. So anyways, 6, 6, 0, 3, that's good. So here, let me go back on the shader. Let me go back to vColor. Okay, because I want to read from the varying or from the attribute, right? From the attribute here in color. And I think that's it. So let's recap. We have this attribute, this extra attribute. for color. Um, this is redundant now. We don't need this. This is for the uniform. We actually don't need this anymore. But we're gonna keep it here just for to avoid any bugs. Uh, but now we're gonna let's work with the cube. We have a cube here specified, and the cube has all the colors for per vertex. So if I draw a cube, it should work, I guess. Let's see. It doesn't work. V color equals to A color. V color equals to A color. And oh, we are missing one line here. gl.enable vertex attribute array A color. We forgot to enable the attribute. Okay, similar to this. Okay. Ooh, that's weird. Huh. That's very weird, but I think I know what happened. This kind of looks cool though. I think I know what happened. Remember, if you have seen this code before, our draw arrays counts the amount. So this line here is the amount of vertices, which is, and again, actually, let me call this. Yeah, it looks kind of crazy, but actually, this should be called geometry now, not triangle. It should be called geometry because now we can draw any geometry. It's not a triangle. So here I get the vertices of the amount of vertices of the geometry. And I was dividing by 3. So what happens is I was dividing this whole list here, the length of this whole list by 3, but what I want is 6, right? Because every vertex has 6 elements. So that's why I think we got this weird looking thing here, because the GPU is trying to draw a different amount of vertices. So it's not closing the whole thing. Let me divide this by 6. Oops, triangle. Oh, here. Sorry. Geometry. All right. What? What did I do? Geometry vertices. Let me see. How did we make this cube? Did we forgot? Oh, maybe. So I have, let me copy, just to make sure. I'm gonna copy the list of cubes, a list of colors and positions again. Maybe there was a bug in here or something. Because let me make sure this is working. Because if we forgot like any semicolon or something here, you could get this weird thing. No, that's not a problem. So I'm gonna go back. Okay, that's not a problem. The cube is not a problem. We did something wrong here. And what is the problem? Let me see. V color equals to A color, V color. Let me see. Are we drawing anything? Let me see. Let me comment this, guys. And here I had Simon, let me see. Here I had geometry divided by 6, set identity. What is the problem? Let me see. False. This is 6, 0, 6, 3. Enable a color, a position. It looks like we, let me, vertices. Do we have any other variable called geometry that is a kind of, so if I had this, let me bring back the rendering function. Maybe I messed up something here. No, there's something wrong, I think, in here. Float size, bytes per element. Oh, I think I see the problem. Wait, let me try. I think we forgot something here. We forgot, let me try. I think this might be the issue as well, one issue at least. We have to enable, we haven't talked about this before, but when we are dealing with 3D shapes, there is this problem of visualizing what is in front and what is at the back. So, but WebGL already takes care of that for us. So for example, if you have one vertex in front of the other, you have to tell the WebGL to consider that, and we have to call enable here. Have to call enable depth test. Let's see if this is the problem. I forgot. We definitely need this here, but this might be one issue. We have to enable this depth test, and then when you clear the screen here, when you clear the screen, you have to clear also the depth. Oops, sorry, depth buffer bit. Oh, depth buffer bit. This might be, we forgot this. We definitely need this here because we have vertices that are in front of the others, and we have to tell WebGL to actually test that, to consider that when rendering. So let me see if this is the issue. This might be the issue. Oh, there you go. That's the problem. Crazy. We forgot this, and that was the only problem. So, whew, okay, let me go back and like have the geometry here because I think this is better, and that's what I wanted. Okay, so we had everything right from the beginning. The cube was right. The setup was right. Everything was right here. Everything was just right. The only issue we had was we forgot to enable the depth test, which is needed whenever you have vertices in front of others. And you have to tell WebGL to consider that, because then to know which color has to be shown and how to do, for example, blending, if you have different alpha channels, how to blend the colors and all of that, you have to enable this. And remember that you have also to clear the depth buffer every time. And I'm gonna do this here as well in this clear. It doesn't hurt. So if you do this, now we have one color per face because we did this in exactly here in this cube. Okay. Sorry about this mistake. But does it make sense? Did you guys understand the whole thing? Yes or no? Yes, I think so. Okay. So sorry, and if you have any specific questions, please let me know. I encourage you to understand this and to play with this code. I'm gonna upload it on Canvas, and I encourage you to play with this and maybe create other shapes like your your circle or a pyramid or something. Exercise yourself or by creating other shapes. I think creating a pyramid would be cool, where each face of the pyramid has a different color. I think last but not least, what I want to show is what happens if you give different colors here. First of all, let's fix our triangle, because if you try to draw our triangle like this right now, you're gonna get an error because we need to specify the colors here. It's now from now on, it's kind of for every shape you're gonna need to do this because we have this configuration here. This configuration is applied to every vertex. We could have different configurations if you want, having kind of a bunch of if statements here and there to check if you want this type of geometry or the other. But I think it's easier to assume that every single shape has position and color per vertex if you are doing this. So because of that, I'm going to get rid of this uniform. That is the color, our old uniform for color. I'm going to get rid of this guy. We don't need this anymore. Okay, so still works. I'm also gonna work. So the triangle. Let's see what happens if you try to draw the triangle without giving any color, right? So if I go to here, if I try to draw the triangle, there's a bunch of problems right here. We are dividing by 6, and now the triangle only has 3 elements per. So I expect to get an error. Okay, if I try to draw this triangle, let's see what happens. Yeah, indeed. Oh wait, because not defined. But let me see a triangle one. Let me uncomment. It doesn't draw anything. Yeah, this doesn't show an error, but it doesn't. It draws something that's probably black because I haven't defined colors here, right? But what we could do, imagine we could specify the color here in the constructor, right? And say, actually, before doing that, we could say here, red for each vertex. Okay. So red, I'm going to make every vertex red. Then now I should see a red triangle. Good. So we have to do the same thing for the square, right? I'm gonna make the square red. Every vertex needs 6 numbers. That's why I'm doing this, right? Every vertex needs 6 numbers because that's how we specified it to be here. Um, Unfortunately, again, this is now true for every vertex. But now if you just add, if you if you add the colors here, now we can also draw. Where is it? A key. We can also draw a square again. I'm gonna uncomment this. We can now draw a square again. See, there's a square in the middle there. So it's a red square. Now every single shape has this possibility of having one color per vertex. So for instance, if I draw the triangle, right? I see this whole triangle in red, but it could have one color per vertex, and let's see that happening. Imagine if here I had blue, and here if I had red. What's going to happen, right? If I have A is the bottom left, so this is red. B is the bottom right, this is blue, and this is green. What happens to the other points inside this triangle, right? If I define three different colors here, let me refresh and show. So it looks pretty cool, right? So again, this is the bottom left, it's red. The bottom right is green. The top point is blue, but it interpolates the colors for us across this whole triangle using barycentric coordinates automatically. We didn't have to do anything. So the fragment shader does that for us automatically, interpolates the data across all the points in this triangle. And this is not only because it's color. Uh, the question here, Soren is asking, can we manually adjust the interpolation amount? No, because interpolation is defined based on distances, right? So there is no, or in this case, you can see it as areas as well for barycentric coordinates, but we can't define like the amounts, right? It's defined to be like this. If you want to play with this, you could by passing other data to the shader, maybe playing with the shader, maybe can use another attribute to pass kind of weights that you multiply. Um, but it's not in the scope of this course to do this anyway. This will be more advanced shader techniques. But essentially, you get this nice interpolation automatically done for us. And note that this was already done for position as well, because we only specify three vertices, but what is the position for these intermediate pixels here, right, or points? So these points were also interpolated for us, right? And perhaps you can see that by doing something kind of crazy, but I want to show you, which is, I'm going to go here on my assignment 2, in my shader. And what if, instead of a color here, what if we put a position here? Right? A position is a vector 3. It's fine. This is also a vector 3. So in terms of types, it's going to work, right? And I'm going to assign vcolor, but vcolor now represents position. So I'm going to use the position to paint the triangle. So let's study this a little bit to see what happens. And I'm doing this to show you that interpolation also happens for position. In a general way, every attribute that is given here and passed to the fragment shader as a varying gets interpolated automatically. So every varying or every attribute gets interpolated in the shader, in the fragment shader. Right, so vcolor here is interpolated across the points. If you had another varying here, hypothetical varying, vector 3, maybe, I don't know, blah, blah, blah. If you had another hypothetical varying here, it will also be interpolated. So this is true for every single attribute. But let me show that working with a position, because we have this is another attribute that we have here that we could pass to vcolor. And let's study this. Let's study this and before seeing the result. Let's look at our triangle. So what's going on here is that bottom left, minus minus 0. This is uh, this vertex. It's now red, but we are telling the shader, the fragment shader, to draw using this color, which honestly doesn't make much sense, right? Because it's a negative color. So this is minus minus 0. So this, so the GPU is going to try to visualize this as a negative color, which doesn't make sense. We don't know this. Same here and same here. Let's see what happens. So this is black, right? The bottom left is black. So it turns out that whenever the value is negative, it's clamped to 0. So this is black because minus 1 becomes 0, minus 1 becomes 0, and 0 is 0. So this is black. So we see black here, right? The second position is the bottom right, is here. And it's red. And again, it makes sense because this is 1, red. This is minus 1, so it becomes 0. And this is 0. So this whole color here is actually red. And the top one is green because, yeah, this is green, 0, 1, 0. Okay, so and we see that in the middle, things get interpolated. But now from black to green, green to red, and in the middle here, you get this mix. I know this is kind of a crazy example, but I just did it just to show that even a position gets interpolated for us. I hope that didn't confuse you. It was just another way. What we want is actually this, because we want to get the last 3 numbers. So if you bring back, we get that nice effect. Again, the best way to understand the whole thing is actually to play with these numbers and see what it does, and play with the shader a little bit, but play with these colors and see what happens. So for example, I could have the same color here for the bottom left. So if I have red and red here, right, and then blue on top, I would get this type of effect. See, now I'm having red, red, and blue. So red, red, and blue. Okay, so I can play with this as much as I want. Let me go back. We could do something similar with the square. We could have here different colors. Like different colors for this first triangle, different colors for the second triangle. And let's see what happens. Let's study this case now. I'm going to go to assignment, so here, and draw the square now. I'm going to draw a square. See what happens. Let's see what happens here. For the first triangle, this is the top left corner. So this is red. Okay, red. This is the bottom left corner, and this is green. Next one is the bottom right corner, which is blue. So this is one triangle. So now the interpolation happens here. See, the interpolation happens across triangles, not across the cube or the square or the face. It happens in this triangle. And I can show you that. So because these two guys, so because this face has the same colors as this face, I get this nice kind of blending from, and so symmetrical, I had this symmetrical effect. But if I messed it up with this, and if I make this, let's say, 1, 1, 1. Now this whole triangle is going to be red. The top triangle is going to be red. See? And again, there's still interpolation going on here. But if you interpolate between the same color, you get the same color everywhere. So it's important to realize that interpolation always happens. But if you interpolate between the same colors, you get exactly the same color everywhere. And also I want to show here that the interpolation happens per triangle, right? So if you study this example now, this bottom triangle, right? Again, top left corner is red, bottom left corner is green, and bottom right corner is blue. So I interpolate from blue to red, red to green in this triangle. Second triangle, I have the top left corner again, the top right corner red, and the bottom right corner red. So interpolation gets the same color. But if I want to mess up, what I could try to do is maybe have this here, kind of the opposite colors. And see that now I'm giving red here as opposed to here. So now I have red here, blue here, and green still uh, in this kind of the opposite direction. But I just inverted the colors here, or the sequence of the colors in these faces. And if you do this for the cube, you're going to see the same effect, but per face. It's just important to realize that interpolation happens per triangle. This is like the takeaway, I think, from this second part of this lab, which is interpolation happens per triangle. Okay, and it interpolates every attribute. So a position and a color. And if you had a third attribute here, it would also interpolate that attribute. Um, that's what I had for today. We